This is lesson 4.4, graphing a function rule. Your objective is to graph equations that represent functions. A continuous graph is a graph that is unbroken. Notice the example, the graph continues and the arrowheads at the end indicate that they continue on, but the graph never breaks. A discrete graph is a graph composed of isolated points. Notice these points are not connected, but this is a graph that represents some data. The set of all solutions of an equation forms the equation's graph. A graph may include solutions that do not appear in a table. A real-world graph should only show points that make sense in the given situation. For example, what is the graph of the function rule y equals negative 2x plus 1? First, you need to make a table of values. So our x is our independent variable, and our y is our dependent variable, which we'll figure out through the function rule, and then we have our ordered pairs. Since this is not a real-world situation, and we're just trying to graph a function, we can choose any values of x. I recommend choosing negative values, 0, and positive values to show a variety of points. Once you've figured out your y values and find your ordered pairs, then you will graph the ordered pairs. So let's graph these points. And we have at negative 1, y equals 3. At 0, y equals 1. At 1, y equals negative 1. And at 2, y equals negative 3. Once you've plotted all your points, you need to connect the dots to create a line. Since the function rule does not just say that these are the only possible solutions, all these points on this line are a possible solution, including all the rational numbers, meaning the decimals and the fractions, positives and negatives. And you must use arrowheads at the ends of your lines to indicate that the solutions go on forever. When you graph a real-world function rule, choose appropriate intervals for the units on the axes. Every interval on an axis should represent the same change in value. If all the data are non-negative, show only the first quadrant. For example, we have in problem 2, the function rule W equals 146C plus 30,000 represents the total weight in pounds of a concrete mixer truck that carries C cubic feet of concrete. If the capacity of the truck is 200 cubic feet, what is a reasonable graph of the function rule? So first you need to make a table to find ordered pairs. Remember though that the truck can only hold up to 200 cubic feet of concrete. So we only need C values that are from 0 to 200. We don't need anything in the negatives because you can't have negative cubic feet of concrete, and you don't need anything above 200 because in this situation the truck holds a maximum of 200 cubic feet. Then we find our weight using the function rule, and we have our ordered pairs. Since C is our independent variable, we'll put that on the x-axis, and I've used an interval of 50 for each line. Our weight is dependent on the number of cubic feet, so that will be on the y-axis, and I've chosen intervals of 5,000. However, since our numbers start at 30,000, remember down here on the bottom of the graph, since we're not using all those numbers, we can use the zigzag line to indicate there's plenty of numbers down here, but we've kind of truncated them. So let's plot our points. At 0, we have 30,000. At 50, we have 37,300. At 100, we are at 44,600, so that's very close to 45,000. 150, we're at 51,900, so a little above the 50, and at 200 we have 59,200. Notice these are all in a straight line. Remember, once you graph them, you need to connect the dots. In this case, we don't need the arrowheads at the ends because 200 is our maximum weight, so our data is not going to go beyond that. And we don't need an arrowhead on this side because we can't have negative cubic feet of concrete. However, you do need to connect the dots because I can have cubic feet of concrete that are between these values. So I can try to figure out what 40 cubic feet would weigh by looking at this graph. And it would be around 35,000. I could try to figure out what 175 cubic feet would weigh, and it's around 55,000. So you must connect the dots to create that line to show all the other possible solutions. Problem 3. A local cheesemaker is making cheddar cheese to sell at a farmer's market. The amount of milk used to make the cheese and the price at which he sells the cheese are shown below. Write a function for each situation. Graph each function. Is the graph continuous or discrete? So, the first table, we have the weight of cheese in ounces depends on the number of gallons, M, of milk used. So W equals 16M. The amount A of money made from selling cheese depends on the number N of wheels sold. So here we have how many wheels of cheese we sold and how much money we make. So let's graph these points first for the weight of the cheese depending on the milk. And remember, any amount of milk makes sense. So even though we've chosen values from 0 through 4, I can technically use 1.5 ounces of milk gallons of milk. I can also use 2 2/3 gallons of milk. So in this case, our graph will be continuous because I can use any amounts of milk. So at 0, let's see, well, first we have our milk here. Whoops. We'll put milk as our independent variable, and then we have our weight as our dependent variable. And then we will need to choose our intervals. So for milk in gallons, I forgot to label that, we will use just 1, 2, 3, and 4. And for our weight, which is in ounces, we will use, let's see what our data points are from 0 to 64, so we could go by tens. Let's do and I need to make this a little bit bigger to fit. Okay, so let's plot our points. Okay, so we have at 0, we'll make 0 ounces of cheese. At 1 gallon, we have about 16 ounces of cheese. 2 gallons, we make 32. 3, we make 48. And at 4, we make 64. Notice this is a continuous graph, So we need to connect these points. Also, I need to make sure I put an arrowhead at the end of my line because I can definitely use more than 4 gallons of milk, but I will not use negative gallons of milk, so I don't need an arrowhead on that side. For the number of cheese sold, or wheels of cheese sold, and the amount of money made, these are points that will create a discrete graph because I will not be selling half of a wheel or 2/3 of a wheel. So I'm only counting the whole numbers. And let's plot those points. So we have number of wheels as our independent variable. And then we have the amount of money made off of these. And for our wheels, we can just use 1, 2, 3, 5. And as for the y-axis, since our numbers go from 0 to 36, we can go in 5s or even 2s. But the 5s would probably fit a little bit better. Remember, you always want to choose intervals that make sense. Okay, so we have at 0 number of wheels, we'll obviously make absolutely no money. At 1 wheel, we're making $9. 2 wheels, we're making 18. 3, we're making 27. And at 4 wheels, we'll make 36. So this is a discrete graph because I'm not going to connect these dots. We cannot solve parts of a wheel, whereas the amount of milk we can use can be rational numbers, so we connect the dots. You can also graph a nonlinear function rule when a function rule does not represent a real-world situation. Graph it as a continuous function. So what is the graph of the function rule y equals x squared plus 1? First, you need to make your values table. For your x values, remember we said choose a variety of numbers. Negative numbers, 0, and positive numbers. Figure out your y values, and then graph your ordered pairs. So at -2, we have 5. Okay, -1, we have 2. 0, we have 1. And then at 1, we have 2. And at 2, we have 5. So this is obviously not going to be a linear function. This is definitely a nonlinear function. But because we can pretty much substitute any value for x, our solutions are really all the points that lie on this graph. So I'm trying my best here to draw a nice pretty parabola for you. Let's see if I can do that again. Okay, it should kind of look like a U almost, but make sure you put arrows at the ends of your graphs because this graph goes on forever and ever. We can plug in any value of x and figure out the y. So this is a continuous function. Here's a sample problem. What is the graph of the function y equals 1/2 x minus 1? Again, we'll make our table, pick any values for x, so let's say -2, -1, 0, 1, and 2. We are going to assume that this is a continuous graph because it's not a real-world situation, and we are going to use all 4 quadrants, so we need to pick x values that are negative. So once we plug that in, we have Half times negative 2 would be negative 1, minus 1 would give you negative 2. We have negative 1, so 1 times a half is negative half, minus 1 would give you negative 1.5, or negative 1.5. 0 would give me negative 1. 1 would give me half minus 1, so I'd be at negative 0.5 or negative half. And 2 would give me 0. So let's plot these points at negative 2. I'm at negative 2. Okay, negative 1, I'm at negative 1.5. 0, I'm at negative 1. And 1, negative half. And at 2, 0. So again, we're going to connect these dots because we're assuming that it is a continuous graph, and any points on this line will be a solution for our function, so we need to make sure we have arrowheads at the ends of our line.